Hola chicos, vamos a tener una lección muy fácil hoy. Ahora estoy aprendiendo el subjuntivo en español. Es difícil, pero mi lección para ustedes hoy es muy fácil. Ok, vamos a empezar. All right. So what I was saying to you was that I have an easy lesson for today. So let's get started. Why is that dark? I'm in a light room. What's going on? Hello? What's going on? I'm going to turn my camera. Well, what if I do a lamp? Hey! Okay. I'm not sure why this is so dark, so I'm going to restart my camera. I apologize. I didn't catch this before I started my lesson. Sorry about this, class. My document camera is not behaving. All right, let's see if it's better now. Hey, that's better. Okay, so this is AP Physics 1, March 5th, period 4. Okay, so today we are going to talk about two types of waves. Okay, so there are two types of waves that you can see in nature. Okay, so one of the types of waves is called a transverse wave. Okay, and a transverse wave is a wave where the medium vibrates perpendicular to the direction of wave travel. So a good example of that is like a water wave. Or I should say a water surface wave. Why is that? Well, if you think about a water wave, the water wave, it's traveling across the surface. And if you're floating in the ocean, which way are you going to move as the wave goes by? You're going to start to bob up and down. Okay? So a wave goes left to right, for example. You bob up and down. Up and down is perpendicular to left and right. So that's a transverse wave. Okay? So another Really good example of a transverse wave, this is probably the classic example of a transverse wave, is electromagnetic waves. So that includes light. So light is a transverse wave. That includes things like radio waves, microwaves, etc. Okay, so those are all transverse waves. So let's go ahead and look at an animation of some waves. So let me pull it up here. Okay. Hopefully you guys can see this. So this is a string, and I am going to create a transverse wave. Okay. And so one of the things you can see, it's a little bit laggy, is clearly the wave is moving to the right, because if we look at the crest of the wave, it's going to the right out the window. But what I want you to do is I want you to focus on one of these green dots, okay? And if you look at the green dot, you'll notice that each green dot is moving up and down. So the wave itself is traveling from left to right, but the medium is vibrating up and down. Up and down is perpendicular to left and right, so this is a transverse wave. Okay? So that was an example of a transverse wave. So there's a nice little mnemonic that I created to help you remember that a transverse wave vibrates perpendicular to the direction of wave travel. And so if you think about transverse, that starts with a T. And if you take that T and you flip it upside down, it looks like that. And that is the symbol in math class for perpendicular. So if you have a hard time remembering that a transverse wave vibrates perpendicular to the direction of travel, that's a good mnemonic to help you remember it. Okay. The other type of wave is called a longitudinal wave. Okay. So a longitudinal wave is a wave where the medium vibrates parallel to the direction of wave travel. So longitudinal waves are parallel, transverse waves are perpendicular. The best or the classic example of a longitudinal wave would be a sound wave. Sound is a longitudinal wave. So let's watch an animation of longitudinal waves. So let's show you. Okay. So this is really, really laggy. I have too many tabs open. There we go. So this is kind of like a slinky. And clearly you can see that the longitudinal wave has these spots where the medium is squished together, okay? And then there are spots where the medium is stretched out. But the main thing I want you to look at is clearly the wave is traveling to the right. And if you look at one of these sections, like maybe this red section, you can see that it gets moved from side to side. Okay? See how the wave is moving left, right, and each section is moving left and right. Okay? So this is a good example of a longitudinal wave, a slinky. So I'm going to reset that. Okay. All right, so I have a mnemonic for okay. I have a mnemonic for longitudinal waves as well to help you remember. Longitudinal waves so if we look at longitudinal, it begins and it ends with an L. So if I put the first letter and the last letter together, it looks like this. And that is the same symbol you use in your math class for parallel. Okay? So when I am drawing these types of waves, I typically would draw a transverse wave like this. Am I doing the wrong lesson for today? I think I'm doing the wrong lesson. I just need to check. I got ahead of myself. I'm pretty sure I did, but that's okay. Because this lesson doesn't have stuff that is that has to do with any of the other stuff we've learned so far. So this is an example of a transverse wave. And so transverse waves, the highest point on a transverse wave is called a crest. And the lowest point on a transverse wave is called a trough. Okay? So that's a drawing of a transverse wave. We can also draw a longitudinal wave. And when I draw longitudinal waves, what I like to do is draw them as kind of vertical lines. And so you have maybe some more here, here. So this is kind of what a, put a few more in, what a longitudinal wave looks like. Okay. These are kind of like the coils of the slinky bunched together, and here are the coils of the slinky stretched apart. And so, so the location on the wave where the medium is squished together, that is called a compression. Okay, so a compression is a part of the medium with higher density. Okay, and then because we're making part of the medium more dense, there has to be another part of the medium that is less dense. So that would be right here, and that is called a rarefaction. So that is a less dense region. So the way I remember rarefaction is that rarefaction has rare meaning not common. So the medium, there's less particles in the medium right here, so the particles are less common. They're rarer. It's a rarefaction. Okay. Another word that you might have heard before is rarefy. Okay, to make less available. So that's how I remember rarefaction. It's kind of a strange word. Okay, so let's talk about what we've learned so far. Essentially, what we've learned is that is some vocabulary terms. We've learned that there is a transverse wave, which vibrates perpendicular to the direction of wave travel. And there is a longitudinal wave, which vibrates parallel to the direction of wave travel. And I've given examples of each type of wave. So the one you probably want to remember for transverse waves is that light is a transverse wave. And longitudinal waves, you'll want to remember that sound is a longitudinal wave. And then we also learned about the different parts of transverse waves and the different parts of longitudinal waves. So there's crest, trough, compression, rarefaction. Okay, so we've essentially learned vocabulary so far. So now let's sort of get into some nitty-gritty. So some mediums, remember, mediums are the thing that a wave travels through. Some mediums allow both transverse and longitudinal waves. Not all of them, but some of them. So here are some examples. If you take a slinky and you vibrate a slinky like this, you are going to create a transverse wave that goes along the slinky. But if you take the slinky and you vibrate it like this, you are going to create a longitudinal wave that travels along the slinky. And I forgot to grab a slinky from my classroom, so I can't demonstrate that. But slinkies allow both. The Earth itself. So any solid material is going to have both transverse and longitudinal waves. So, Earth's crust allows both transverse and longitudinal waves. Okay? And then there are some mediums that only allow one type, only allow one. So, for example, air only allows longitudinal waves. You can't have a transverse sound wave. The air just does not allow transverse waves. But if you have a medium that allows both, if a medium allows both, okay, then they will have different speeds. Okay, so in general, there might be some medium where they have the same speed, but most of the time the longitudinal wave is faster, usually. Okay, so we can actually use this. So I wanted to do an example with earthquakes. Okay. So let's suppose that the velocity of transverse waves through the Earth's crust, and I'm just making up these numbers off the top of my head, is 1,000 meters per second. Okay, and let's suppose that the velocity of longitudinal waves through the Earth's crust is 2,000 meters per second. Okay, so let's suppose an earthquake happens. Okay, and so obviously if an earthquake happens, then you are going to feel the longitudinal waves before the transverse waves because the longitudinal waves traveled faster. Okay, so an earthquake generates both longitudinal and transverse waves, but you feel the longitudinal first. In fact, if you are experiencing an earthquake and you're not terrified and you actually have a moment to think, you can actually feel the arrival of each. So there's kind of like an initial shake and then a second shake. Okay, and that's the arrival of both types of waves. An earthquake happens. And let's suppose that the transverse waves arrive, let's say, 4 seconds later. Okay? 4 seconds later. How far away was the earthquake? So we can actually use this information to figure out how far away the earthquake is. So here's what you would do. You would write a delta x equals velocity times time. Okay, you are going to write one of these equations for both the transverse wave and the longitudinal wave. So for the transverse wave, okay, for the transverse wave, we have delta x, which is unknown. We don't know how far away it is. We also don't know when the earthquake happened. Okay, so for the transverse wave, actually, I'm going to do longitudinal first. My bad. So the longitudinal wave travels at 2,000 meters per second, and we know it happened some time t ago. Okay. Now, if we do the same thing for the transverse wave, we know that the transverse wave went from the epicenter of the earthquake to you. Okay, so it has the same delta x as the longitudinal wave, but it has a different speed. Okay, and we know that however long it took, okay, however long it took for the earthquake to, I'm confusing myself. We know that it took 4 seconds more. So if the longitudinal wave took t seconds to arrive, then the transverse wave took t plus 4 seconds because it arrived 4 seconds later. So I hope that makes sense. So now I'm going to distribute. Well, what I'm going to do is I'm going to set the two delta x's equal to each other. So I have 2,000 t equals 1,000 t plus 4,000. Okay. And then I can take the 1,000 t and subtract it. So I have 1,000 t equals 4,000. Then I divide both sides by 1,000, and I get that t equals 4 seconds. Okay. So that is the earthquake occurred 4 seconds before when the longitudinal wave arrived. Then what you would do is you would plug that back in to either one of the equations. All right, so I'm going to plug it into the top one, and I get that delta x is 2,000 times 4, which will be 8,000 meters away. So that earthquake occurred 8,000 meters away. So that is how it works. So then, if you have a detector of earthquakes, you know those little things that have the piece of paper, and then as the earthquake hits, it like scribbles on the piece of paper. I can't remember what they're called right now, but you know that if that's the location of the detector, the earthquake happened somewhere in a circle that is 8,000 meters in radius. So it occurred somewhere along here. So then what you do is you have a second detector. The second detector is over here, and the second detector does its own calculation, and it thinks that it's on a circle that's this far away. So, and then there's a third detector, and it thinks that the earthquake is this far away. So we can see we have 3 detectors, okay, and they are all able to calculate how far away the earthquake was from them, okay. And so they all do their own calculations, and because the detectors are at different locations, they're going to see that the earthquake is a different distance away, okay. But if we have multiple detectors, we can see that the only spot that is consistent with all of the detectors is right there. So that is how we determine the epicenter of the earthquake. Okay? So that determining the epicenter of the earthquake relies on the fact that we know how fast transverse waves travel and longitudinal waves travel, so we can figure out how far away earthquakes are. And then once we do that, and we have multiple detectors, we can locate the exact spot where the earthquake happened. Okay? So when you see it on the news, they say the earthquake happened here. That's how they know, which I think is kind of neat. Okay. So next, I want to talk about longitudinal waves a little bit. And if you have a longitudinal wave, let's suppose I have a d of x function for a longitudinal wave. So let's say that d of x is, let's say, 3, actually I'm not going to say 3, I'm going to say 0.3 cosine of x. So if d of x is positive, so remember, the way that longitudinal waves work is they vibrate the medium parallel to the direction of wave travel. So if d of x is positive, that means that the medium was displaced forward. And if the displacement as a function of position is negative, that means that the medium is displaced back. All right. So let's suppose I have 2 positions, and this is the position x equals 0, and this is the position x equals, let's say, 1 meter. So 0 meters, x equals 1 meter. The distance between these 2 points before the wave would be 1 meter, because 1 minus 0 is 0. But once the wave travels through the medium, okay, it distorts the medium, so the distances change, right? If two parts of the medium are in a compression together, they got moved closer together. So whereas the distance before the wave traveled through the medium was this, when the compression hits them, they're going to be closer together. Okay? So it distorts distances. When a rarefaction passes through the medium, they're going to be further apart than they were before. Okay? So let's evaluate what is d of 0. Okay? And so that is going to be 0.3 cosine of 0, which is 0.3 meters. Okay? So this part of the medium, and it's plus 0.3, gets pushed forward. Okay, I'll make a X with a circle. And now this part is going to be at 0 plus 0.3. So this part of the medium is now at x equals 0.3 meters. Okay? Now let's look at this point. Where does this point get moved to? So what is d of 1? That would be 0.3 cosine of 1. And for this calculation, I want my calculator in radians mode. Okay? So I have, so that's 1 radian. So I have 0.3 times cosine of and I get 0.16. So plus 0.16 meters. So that means that this part of the medium got displaced forward by 0.16 meters. So if we take 1 meter and we displace it forward by 0.16, it is now going to end up at x equals 1.16 meters. Okay? So as the wave is passing through, the new distance between these 2 points is going to be 1.16 minus 0.3 equals 0.86 meters. All right? So, as a result of the wave traveling through, at this particular moment, these 2 points, which were 1 meter apart, are now only 0.86 meters apart. So they got compressed. So at this particular instant, these 2 points are in a compression together because they are less far apart than they were before. Okay? So you need to know how to interpret displacement functions if it is a longitudinal wave. Let's talk a little bit about transverse waves. Okay. If we think about transverse waves, the transverse waves are vibrating perpendicular to the direction of wave travel. Okay. But if you think about it, there are two possibilities. Okay. If I have a wave that is traveling towards the camera, that transverse wave could be vibrating up and down like this, or it could be vibrating side to side like this. So there are two possibilities for transverse waves. They can vibrate vertically or they can vibrate horizontally. Okay? So these two possibilities are called polarizations. Okay? These are called polarizations. You can have the vertical polarization, or you can have the horizontal polarization. All right? And so the vertical polarization would be the one that's going up and down. The horizontal would be the one going side to side. That's assuming the wave is traveling towards the camera. Okay? So what do you think happens if you superpose? Because you can have two waves superposing where one is vertically polarized and one is horizontally polarized. In that case, you have a combination of an up-down motion and a side-to-side motion, so the wave vibrates diagonally. Okay? So diagonal wave is a diagonally polarized wave is a superposition of vertical and horizontal. You can also get really weird things like where the medium does spirals, like this. And that is a superposition of vertical and horizontal. Okay? So what if I have, so at a particular moment, okay, you have a vertically polarized wave, and its displacement as a function of position is, let's say, 3 sine of 2x. Okay? And then you have a horizontally polarized wave. Its displacement as a function of position is 2 cosine of 3x. Okay? And so these two waves are in superposition. Okay? And so what I want to know is how far is x equals 1 displaced by the wave. All right? So what I'm going to do is I'm going to find the vertical polarization evaluated at 1, and then I'm going to find the horizontal polarization evaluated at 1. So the vertical displacement at 1 is going to be 3 sine of 2. Again, my calculator is in radians mode for this calculation. And I get 2.7 meters. The displacement of the horizontal wave is, again, I plug in 1, but for the different equation, 2 cosine of 3. And I get negative 2 meters, just about. Okay? So what does that mean? It means that the medium as a whole is displaced. So if this is the original spot, when the wave travels, this point is displaced up 2.7 meters. Okay? And then it is displaced to the left 2 meters. Up 2.7 meters and then to the left 2 meters. So how far did this point move from where it was originally? It moved from here to here. And this is a right angle. So if I want to know how far is this point displaced, I would use the Pythagorean theorem to figure out what this distance is. Okay? So that's going to be square root of 2 squared plus 2.7 squared. and that is 3.4 meters. So the total displacement due to the passage of that wave of x equals 1 is going to be 3.4 meters. So it's going to move that far from where it started. Okay? And that's at that particular instant. Because remember, these displacements are changing because waves move. The displacement as a function of position moves. So that's why it's important to say at this particular moment. Okay? So that is my lesson for today, and I will